Next, we'll look at finding the arc length of a parametric curve. So we can start with our notion of arc length for a function y equals f of x. Which we have shown previously is equal to the integral from a to b of the square root of 1 plus dy dx squared. And we can think of how this might now transform into the integral for arc length with a parametric curve. So one way is to take the expression that we have here, 1 plus dy over dx squared dx. This is our arc length differential. If we express dy over dx in terms of its derivative for the parametric curve, we can write dy over dt over dx over dt. And in this case, if we were then to manipulate this a little bit, we can write this as dx over dt squared plus dy over dt squared, where on the outside now we have dx divided by dx over dt. And then finally we can simplify dx over dt as, dx over dt as just dt. Which now we can see that the arc length differential ds expressed in terms of the parametric equations gives us this formula here for the arc length of a parametric curve. So that is, if I have a parametric curve where the endpoints are given by f of alpha, g of alpha, and then f of beta, g of beta, then we're going to integrate from alpha to beta of square root of dx over dt squared plus dy over dt squared, or here in terms of f and g, it's the square root of f prime of t squared plus g prime of t squared. So there it is. And it's also worth noting here that the functions f prime and g prime need to be continuous on the interval alpha to beta. And the curve C must only be traversed exactly once, otherwise if it's traversed more than once, then you might get a longer, a larger value than it should be. So let's think about how it might apply in this case. Suppose we want to find the arc length around the circle given by x equals cosine t, y equals sine t. So it will be the integral from 0 to 2 pi square root. So x prime squared plus y prime squared we'll take the derivative of our x equation, which is negative sine t, and then the derivative of our y equation, which is cosine t. So we have inside the square root sine squared plus cosine squared, which we know is equal to 1. Square root of 1 is 1, so we're just taking the integral from 0 to 2 pi of dt, which is just t evaluated from 0 to 2 pi. So it's 2 pi. And of course that agrees with what we know about the circumference of a circle of radius 1. How about finding the arc length of one arch of our cycloid? So again here, let's remind ourselves, one arch of the cycloid goes from 0 to 2 pi. So we'll integrate from 0 to 2 pi. And let's take x prime and y prime. X prime will be r times 1 minus cosine theta. Y prime will be r sine theta. So we'll put those values in. We've got r times 1 minus cosine theta squared plus r times sine theta squared. And then let's simplify it so that we can evaluate it. First I'll FOIL this first one out. 1 minus 2 cosine theta plus cosine squared theta plus r squared sine theta, r sine squared theta. We know that I could factor the r out from these two terms, which will just be r on the outside. And then we're left with cosine squared plus sine squared, which we know that'll equal to 1. So we'll have 1 plus 1 gives me 2 there. And in order to evaluate this, it might be worth thinking about an identity that we can use to simplify this square root. So to remind you, we have this identity. Cosine squared is equal to, well, actually here, let's do the one for sine squared. So if I have sine squared x, that's 1/2 1 minus cosine of 2x. And let's see, that almost looks similar to what we have here. Let's write a 2 sine squared theta, or sine squared x, equals 1 minus cosine 2x. I can multiply by another factor of 2, so we get 4 sine squared x equals 2 minus 2 cosine 2x. Okay. So 2 minus 2 cosine theta would be what I would have if I put theta in for 2x. So if 2x is equal to theta, then x is going to be theta over 2. So this would be 4 sine squared of theta over 2 is equal to 2 minus 2 cosine of theta. And now writing it like this, I can take the square root of it, and because it's got this sine squared factor, it'll simplify the square root. Okay, so that little trick there with the trig identity now gets it into a form where we can evaluate. So I'll have 2r integral from 0 to 2 pi sine of theta over 2 d theta. Notice I just took the square root of 4 is 2 on the outside, and then the square root of sine squared gives me sine. And now when I evaluate the integral, we get negative cosine of theta over 2 divided by theta over 2, or divided by 1/2 actually. So multiplied by 2. I'll just multiply by 2 out in front. And then we'll evaluate from 0 to 2 pi. So we have 4r. Negative cosine of 2 pi over 2 is cosine of pi. So negative cosine of pi, and then minus negative cosine, so plus cosine of 0. Remember, negative cosine of pi is negative 1, so that's 4r times positive 1 plus cosine of 0 is also 1. So there we have it. 4r times 2 is 8r. So that little trick with the trig identity makes that integral a little bit simpler to evaluate. And then finally we have an extension on that idea. We know that if I'm looking for the surface area of a surface of revolution, we can use the arc length differential ds that we've derived for parametric equations to get the surface area of a surface formed by revolving a parametric curve. So in this case, if we take our parametric curve and revolve it around the x-axis, this will give us the area of the surface that's formed. So let's use that to show that the surface area of a sphere of radius r is 4 pi r squared. So we can form a sphere by revolving the circle of radius r about the x-axis. Okay. And we know it has parametric equations, x equals r cosine theta, y equals r sine theta. Okay, actually, I'm going to use the parameter t instead of theta. And then theta going from 0 to pi. Or sorry, t going from 0 to pi. And notice I'm only going to pi because we're not going all the way around the circle. We're just doing a semicircle, because when I revolve a semicircle around, it's going to form the full sphere. Okay? So here our surface area will be integral 2 pi y ds. So we'll integrate from 0 to pi. 2 pi, our y equation was r sine t. And then the square root of dx over dt squared, so that's negative r sine t squared, plus dy over dt squared, so that's r cosine t squared. So notice I'm just using the derivatives here. In our equation for the arc length. Okay, so then this, of course, simplifies. We've got r squared times sine squared t plus cosine squared t. And then, of course, this this just becomes 1. So we have the square root of r squared, which is r. So I've got the constant 2 pi r times another factor of r here. So then we're integrating from 0 to pi sine t. Okay, all this other stuff simplified to a constant. And then we've got the integral from 0 to pi of sine t. Integral of sine t will be negative cosine t, evaluated from 0 to pi. So negative cosine of pi minus negative cosine of 0, so plus cosine of 0. So that'll be negative, negative 1, so positive 1 plus 1. So that's 2 pi r squared times 2 is 4 pi r squared. And there we have it. So we've shown that When I revolve this semicircle around the x-axis to form a sphere, it has a surface area of 4 pi r squared.